Okay, so next I'll give a small presentation on causal inference and some concepts of causal inference. Okay, so I guess Jen Xuan, she presented a lot of terminologies that has been hard for me to, or at least it was hard in the past to understand, because it sounds kind of different from what you learn usually in statistics, causal inference. So I'll try to explain what those concepts mean, and try to connect them to what we learn on Tuesday. So it turns out that a lot of the things that we learn in machine learning and statistics and AI is, as you probably know, correlational. So how is this related to that? It's something that we don't usually think about. But there is a lot of interest in this area of causal inference, especially now that we have so much observational data from social media, especially. I know that there are several groups in Facebook, Microsoft, that are trying to take these ideas and apply them to these vast observational data sets that they have, especially related to A/B testing of websites, or trying different ranking algorithms. So I think I read statistics that every day Google runs hundreds of thousands of experiments, basically. So every time you visit the Google search engine, they're trying something different. So in a sense, they're running these experiments, and they're using causal inference to try to understand how to change, or how to make the search a better experience for you. So it's very relevant from that point of view. And of course, we would like to find relationships in the data that are correlational, that are causal, not correlational. So now, when I started learning about this, one of the challenges was that there were like two camps. And maybe if you have a background in computer science, maybe you're familiar with another camp that is led by a professor from UCLA, Judy Apparel, and he has this framework called Do Calculus, and separate, or not separate, but I guess it was developed almost independently from the potential outcomes framework that Jen Xuan was talking about, but they are basically the same. So for a long time, I was a little confused about it. It seemed like one camp was using one set of methods and another camp was using another set of methods. So yes, so you feel my confusion too. Now, I'm not an expert in these things. I'm learning them, and it's just, again, it's sometimes it can be counterintuitive, because we are trying to reason about things that didn't happen and cannot possibly happen. So they're all, in many ways, philosophical questions. Okay, and then I'll give like a very simple example on the Titanic data set, probably your favorite data set, and hopefully that will open your mind to other possibilities. And from what I've seen in Science of Science, I know that the Shun, Aaron Closet, they have applied, Cassidy, they have applied causal inference. Yinding has a nice review paper on causal inference for Science of Science. And I think a couple of days ago, I saw a group from, I don't want to mess this up, but there was like some causal analysis of citations. So the people are starting to apply these ideas to Science of Science. So I'm sure it's going to be very relevant in the next year or two, or sooner than that. All right. So again, when we apply machine learning and AI, we usually are worry about prediction. So if you read a paper in NeurIPS or ICML or any AI, news headlines, it's all about this machine learning achieve superhuman accuracy. But in our kind of studies, we usually are interested not just in the prediction, but in the kind of prescription. What should we do to change behavior? And so that's the causal question rather than just prediction question. So we could have a model that is, extremely accurate, but that doesn't mean that it will give us insight into the causal relationship between things. So now we've come a long way in causal inference. Now there are actually packages that allow you to load causal graphs and query and use data. And there is this nice package in Python that Microsoft has that combines potential outcomes and do calculus. So it combines these two camps. So it's a nice package, and I will recommend. But before you understand what they are doing in that package, you need to understand a little bit of the language that they use and the question and the concepts that they're using. So these are a handful of things that you might want to ask. This comes from the Microsoft group. They're trying to think about things like how people use their products, how people use search engines, with recommendation systems and things like that. So these slides are mostly based on this book. This book is freely available. This is from I think he's an economist, so he takes more of the potential outcomes approach and a lot of the statistical methods, but he mentions also DAGs, directed acyclical graphs, in his book, and he's a good, and he has code in R and Python too. So let me motivate you by this nice example that I saw on the internet, of course. Suppose that you have these 3 data sets. Well, it's the same data set. So if you look at the data, it's the same thing. So you have an x-axis, let's say something that you observe, and then you have a y-axis, this is an outcome. Okay, so this could be like a supervised learning problem. And let's say you're trying to understand whether X is causing Y. Okay, so that means if I change X, well, that can mean many things. So basically, is the change in X causing a change in Y? Okay, and you probably thought about examples, but one of the silly examples that are mentioned sometimes in books is the relationship between the thermometer in your, let's say you have a thermometer in your room, and the temperature outside in the real world. Well, the temperature outside, like the actual weather, is influencing the thermometer. So Y will be the thermometer, and X will be the temperature. So so in that case, well, if there is a change in the temperature in the real world, there will be a change in the thermometer temperature, right? But this doesn't tell you the other way around. Like it doesn't tell you that if there's a change in the thermometer, will there be a change in the temperature outside? And we know from our experience and from our knowledge that's a silly question. But when you have data sets like this, it's hard to tell, or it's like impossible to tell sometimes. So if you have a data set of a thermometer and the temperature, or the weather, you cannot infer these things. So here we have 3 examples of data, and this is Python code, so that's nice, of data that was generated by a process. Okay, so so basically this process is saying, okay, I'm gonna first generate X randomly, and then I'm gonna generate Y by plugging the values of X that I will generate. So basically this is saying, in a sense, that X is generating Y. So there is a causal relationship. Here's the opposite. So first we generate Y, and then we generate X, but it still generates the same data. And here we have another kind of relationship, sometimes called a confounder, where we have an intermediate variable that gets generated first, and that affects X and Y. So depending on how you frame the question, in reality, there is no direct causal effect between X and Y or Y and X. It's just happening through a confounder. Okay, but the data is the same, so it's hard to infer what's going on. Now, I didn't think about this example. You have to go to this website, but it is a clever idea. Okay, so I will present the potential outcome framework, and it has, unfortunately, all these fancy names that I don't think help. It's just a way of thinking about alternative worlds. That's what you have to think. Imagine that something that whatever we are observing in the real world, whatever data you have, is an instantiation of something that could have happened, right? So, so imagine the following. Imagine that we are trying to, and I just give you example directly. So we have let's say in the healthcare setting, we have a patient that has cancer. Okay, we are in the hospital, and there is a doctor that is trying to decide the treatment for this patient. Okay, and we'll have two treatments. We'll have a treatment that is give the patient chemotherapy, so no treatment basically, or surgery, operate the patient, remove the cancer. Okay. So the potential outcomes framework says, okay, depending on the treatment, so this whether to do surgery or not, we will measure something as a result of that. Okay, so we'll try to measure the experimental effect of the surgery on the outcome for that patient. Okay. Now the outcome here in this example that I'm giving you could be how many years, let's say, the patient will live after the operation. And hopefully we want to decide, should we maybe do surgery because it will live, twice as long if we just do chemotherapy. So the notation that they use in the potential outcome framework is as follows. So they say, okay, Y is the outcome, okay, it's the years of additional life. I is the unit, so it will be a patient. And then they use this superscript. 1 means what happens when the patient gets treatment, okay? And 0 means what happens when the patient doesn't get the treatment, so it gets just chemotherapy. Now, what's I guess the unintuitive thing is that we have an outcome for the patient in 2 alternative worlds. Okay, when the patient receives the treatment, and when it doesn't, the same patient, the same Y, doesn't receive the treatment, and that's the confusing part. So to reason about what happens with all these techniques that Jin Xuan was talking about, and the do calculus, and if you've heard of regression discontinuity, all these methods, what they're trying to do is they start from these definitions to derive what are the effects of what you do statistically. Okay, but you have to make assumptions because you cannot observe 2 outcomes. You either observe, if you operate someone, you observe the result of the operation. If you don't operate someone, you observe the result of the non-operation, but you cannot observe the opposite, right? So we can only observe one state of the world. Now we will have another variable called the actual outcome, like what actually happened in the actual world, our data. And that's different from the potential outcomes. Okay. Okay, something happened here, something fell, but let's continue. We shall prevail. So to think about the potential outcome and the actual outcome, we will define another variable called D, which is an assignment variable that will say DI will be 1 if the unit was assigned to treatment. So if the doctor decides, yes, you will get surgery for patient I, then D of I will be 1. Okay, so now we can relate the actual observation of the world, like the actual number of years of the patient, Y I, with this little equation here, which is basically saying if the doctor decided that the patient should get operated, then we will observe the potential outcome 1. If not, we will observe the potential outcome 0. Okay, so, and we cannot observe both. That's the definition. So what we would like to measure, or many of the things that we would like to measure, are what is the difference. And here's the tricky thing: what is the difference from the same unit, like the same patient? What is the difference between operating the person and not operating the person? And of course, again, because we can only see one state of the world, we have to apply all kinds of heuristics and maneuvers to estimate this. And that's the whole enterprise of causal inference. That's why it's called inference. It's not that we're trying to prove anything, because everything we do is just inference. We cannot really prove that it's true. So Jin Chuang was talking about the average treatment effect, and that's simply the expectation. So we take all our subjects in our data set. What is the expected difference between the potential outcome of applying the treatment minus the potential outcome of not applying the treatment? And expectations work in the following way. So if you have an expectation of summation of subtraction, you just you can separate the two. So you can take the expectations separately, but they are the same. They're the same units. But you cannot do this because you don't observe the state of the world for the person. So this is impossible, and this is sometimes called the fundamental problem of causal inference. Now, there are other quantities that are sometimes interesting and also impossible to measure, but they're interesting. So one of them is like, if I apply, what is the treatment effect if I for the people for if I choose to apply the treatment to someone? Okay, and it's again a little tricky because we're saying, okay, if I choose to apply the treatment to unit I, okay, so this is the doctor saying you should get surgery. We want to measure the difference in the potential outcomes. Okay, we will observe this. This is the potential outcome of actually getting the treatment, but we won't observe this. But we'll still like to know, right, the difference between the two. So this little expectation here is called sometimes a counterfactual, because it means we apply the treatment to a subject, but we want to see what would have happened had we not applied the treatment. Okay, so it's in the alternative world, perhaps in a physically multiverse world, what would happen with that patient? Now the treatment, the effects of people that for which we apply the treatment might be different from the average treatment effect. So if I go back, might be different because there might be a relationship between the assignment. Let's say if we give the treatment to someone, there might be differences in how that person reacts. It might be like a correlation there. And my favorite example and very relevant is that people that were in the trial for COVID-19 vaccines, they usually were like scientifically oriented, and they're probably more educated than the general population. So there was a relationship between getting the treatment and these two quantities. Okay, so the counterfactual for those people probably would have been better prospects than just that random population, because they had more education and things like that. Sometimes we are also interested in the opposite, like what is the average treatment of the untreated? Like what happens with the people that we don't treat? What would be the average causal effect condition on the fact that we don't treat them? Now, none of these three things we can observe. So let me give you an example with actual numbers. And again, this is taken from the book. So this is a fake data set because, again, we cannot observe the the potential outcomes. So let's assume that we have 10 patients and we have the potential outcomes. If we operate the patient 1, we get 7 more years. So if we take that 2 more out, so the cancer, we get 7 more years of life. If we just do chemotherapy, it will be just 1 year. So the treatment effect is 6 years, the difference between the two. So we have the full data set here. We are somehow we are God and we can see both outcomes of the world. So if we take the average of this, it's just the average of this minus this, it's 0.6 years. Okay, so the average treatment effect is 0.6 years. Now, let's assume that we have a perfect doctor, in the sense that this doctor somehow knows what is the best treatment for each patient. Okay. Now, this is just, I just want to show you that observational studies differ from the actual causal studies because of things like this. If we have like correlation between the choice of the treatment and the outcome, that's what Qin Chuan was talking about, the unconfounded assumption. Yeah, Theoly, yes. Yes. So we have D, which is the choice from the doctor. So D1 would be, yeah, let's treat you. So if I go back, I'm going to go back one slide. So if I choose to treat patient 1, then I will get to observe 7, because that's the potential outcome for treatment. If I don't choose to treat patient 2, then I will get the potential outcome 0. So that's not treatment. So 6. So this is the data that we will get to see in the real world, right? Now, for this case, because the doctor is kind of having this correlation between the decision and the potential outcome, so there is that relationship, and this is where I think one of you asked, what is this idea of unconfounded? I forget the proper name, but unconfounded something. Is the fact that sometimes you have a relationship between your choice D and the potential outcomes. And that happens very often. Like again, the COVID-19 vaccine, probably in the experiments, people that got the vaccine in the trials were people that were like, they thought they will get better, right? So there is this correlation. So I will measure all these quantities, and I can do it because this is a fake data set, and I'm God. And I get to see these quantities. Now, if we see the naive observation, what's interesting is that with the naive observation, if we just see the data, so we take the average, if we see the average of the people that got the treatment minus the people that didn't get the treatment, we actually get a decrease in life expectancy. Okay, so using observational data, we actually get the opposite conclusion. So what's going on here? And here's where all the methods stem from. What's going on here is that the data that we observe, so this quantity here is just the average of the people that got the treatment, the average outcome, the thing that we observe minus the average observation of the people that didn't get the treatment, is going to be mathematically equal, given the assumptions that we made, to the average treatment effect, which is what we want. Remember, this is what we would like to know. This has the potential outcomes, but it has these two biases. Okay, so the observation, essentially, what this equation is saying, the observation has biases, and the whole idea of causal inference is to get rid of these biases. Okay, so all the methods that you see out there, from the oldest propensity score matching to the newest, I think it's called coerced. There are deep learning methods for causal inference. They all are just trying to get rid of these things with various assumptions and clever ways of doing it. Now, what are these two terms? So selection bias is what I was mentioning. Like sometimes you get sometimes there are differences between the groups that get the treatment. So basically, you get the treatment because of something else, not because you were assigned to it randomly, but because you went to the doctor and you got the treatment. And so the people that don't get the treatment are like a different type of population compared to the people that didn't get the treatment. So you have this selection bias. And then you have this other idea. It's called heterogeneous treatment effect bias. And the idea of this is that there is a difference between getting treated and not getting treated, counterfactually. And we weight that by this, the number of people that, or the proportion of people that didn't get treated on that pie. So we can make some assumptions to get rid of some of these biases. So for example, we can say, we can, if we assume that all the effects for each of the individuals is the same, we can get rid of this term, this bias, okay? But that's not always true, right? I mean, probably never true, but it seems we can maybe get away from it. But this selection bias is just very real, and it happens all the time. You get a treatment because, you know, because of these other causes. It's not because you just are randomly assigned to treatment. So the simplest approach, I call it here in quotes, to try to get rid of this issue, to get rid of the selection bias, is to assume that the selection of getting the treatment is uncorrelated with the potential outcomes. I think this is supposed to be uppercase, superscript. So I can just fix it in real time. So if you have this correlation, if this means it's conditional independence. So if given the treatment, then it's independent. Sorry, independence. This means independence. So if probabilistically independent. So it doesn't. The choice of the treatment doesn't depend on the outcome. So you're not trying to guess if you will get better if you get the treatment. Now, in our case, because we had like a very convoluted example, the doctor was choosing D based on knowing that what will be the best potential outcome for you. So this was not true in the example, and that's why there was such a big discrepancy in the results. Now, almost all cases of our in Science of Science and almost any study of human behavior, this is not true, because humans are making very sophisticated choices based on guesses about what they will, you know, how well they will fare in a certain choice that they will have or in some assignment. So this is almost never true. So that's, therefore you have to make adjustments. Now, let's assume that we have randomization. That's usually what happens with randomized control trials, RCT. In randomized control trials, you get assigned to a treatment randomly. So D is independent by definition of the potential outcome. And this means mathematically that these two quantities are true. So the observation, the expectation value of the observation minus the counterfactual is 0, because you just get randomly assigned. So on average, it will be the same. So there is no selection bias. Okay, so if there is no selection bias, then these two quantities go, the difference between, there is no heterogeneous treatment bias, so because everything is just randomly assigned. So therefore the observe, if I go back to the equation, this is 0, this is 0. So the observe effect of the treatment is going to be the same as the average treatment effect. So you're good to go. So randomization, of course, is not always possible, and that's the whole idea of what we're doing, causal inference. We would like to use observations in Science of Science, of funding, of citations, to make inferences about causal effects. Now, there are other assumptions philosophically. We need to assume that all the units, when they're treated, receive the same amount of treatment. So they're like homogeneous in that sense. That this is also not always true. Like some doctors, for example, in the cancer example, some doctors are better than others. The other big assumption, and especially this is not true for social networks, is that there are no externalities. So if a unit chooses a treatment, that doesn't affect other units. But of course, if you're doing research in network science and in any thing where you have like a social interaction among units, this is not true. So I mean, with vaccines, it's very obvious. Like if we have a portion of the population that doesn't get the vaccine because of epidemiology factors, there will be a cluster of other people that will get affected. So we have externalities. And the third assumption is that we don't have general equilibrium effects. So that means that whatever we observe in our data can be generalized. Basically, there won't be like a change. There is no like a changing factor underlying our observation. It's going to be the same. All right. So now what we will do next is, okay, we have this issue of selection bias. We have to deal with it in some form. So what I will do, I will present a language to describe how variables are related causally in the world. And these are models. So these are things that we get from our experience. And I think philosophically or mathematically, we cannot really infer this from data. So these are assumptions about how the world works. And based on these graphs, we'll detect what are the things that we have to observe and fix so that we can make causal inferences. Okay, and this is something called meeting the backdoor criteria, close all the backdoors in our data set. So basically make the unconfounded effects go away or something like that. I forget the proper name of that. So I will introduce this idea of directed acyclic graphs. The idea is that these graphs represent random variables in our world and causal relationships. Okay? These are not, if you're familiar with probabilistic graphical models, this is not the same. These are causal graphs. Okay, so they actually describe causal relationship. So we don't want like, yeah, so we'll see examples of when we want to, what are the things that we would like to measure so that we close loops in the graph. So, so let's take a look at a couple of examples to see what are the kinds of things that we have to guard. So let's say D is the treatment, the assignment. Okay, so D will be whether the person got surgery or not. Y will be what is the years of additional life after the treatment. And X could be an external variable. In this case, this is called a confounder because it's affecting both D and Y. Okay, so there is a causal effect between D and Y, but there is also some influence from X, from an external, from a variable, a random variable outside. So maybe this is like a variable saying this person is has more risk-taking behavior. Okay, so X could be how much risk the person takes. So if the person, you know, takes a lot of risk, maybe that influences the chances of the person wanting to have a surgery. So the person might be like, yeah, let's take it, let's have the surgery. I don't care. But because the person also takes a lot of risk, maybe we'll have more chances of getting cancer just because of. Well, it will influence the number of years that the person will live after the treatment. So we say that we have different paths, different causal paths. We have a direct path between the treatment and the outcome, but we also have this thing called backdoor path. Okay, and the backdoor path is something that you can go from the treatment to the outcome through an intermediate variable through which you can go in the opposite direction of the arrow. Okay, so if you can go in the opposite direction of the arrow, and so the rules are you can go in the opposite directions of the arrow, and then from X you can go to Y. Okay, so this is called a confounder, and this creates biases because again we can have this idea of risk taking that will affect both the chances of you getting the treatment and the how many years you will live. So that's a backdoor that is open, and here we have another example that is worse in a sense because sometimes we have things that we don't even observe. Here at least we we have some, let's say, some procedure for measuring how much risk you're willing to take, but sometimes we don't even have that procedure. So or we are not even able to measure it. So we will have sometimes confounders that we cannot control for. So that backdoor will be open. So the whole idea of these DAGs is to try to close these backdoors, like try to say, what are the things that we have to measure, control for, so that we can apply causal inference. Sometimes you have things like this, which is different. Like, and I don't have like an intuitive example, but you can have something where the treatment affects some random variable, and also the outcome affects the same variable. Okay, so this could be something like maybe how many, how much how much you can work, right? So if you get a, if you get surgery, maybe it will affect your work, and if the number of years that you get to live will also affect how much you can work. So this could be a variable that gets affected by these two factors. Now, this is also a backdoor path, okay? But this is a different kind of backdoor path. This is close because you have these two arrows, and this is related to joint distributions of random variables. But basically, graphically, it's very easy to detect because you have a path that is hitting this variable from both sides. So basically, whatever is happening here, it won't influence D and Y. Okay, so this is called a collider. Whatever thing goes from D and tries to go from D to Y through this path, it will get blocked by X. Now, there are two problems here. So if you have an open backdoor, you have to close it by conditioning on it. Okay, so let me go back. So this is an open backdoor because we have influence from D to Y indirectly through X, and we have to close it. That means that we have to condition on it, not in a statistical sense, but in a causal inference sense. And I will show you one way of doing that later. Okay, so we have to close that, and then we can do causal inference. If we have a backdoor that is closed, like this one, if we condition on this, so if we make a mistake, we say like, okay, we need to control for how much the person is working, let's say, then we will make a mistake. We will actually open the door, and we will create an influence from D to Y through X. Okay, so we have to be extra careful about what are the things that you have to control for, right? Sometimes you control for some variables and you mess up the causal structure of the data. And sometimes you don't condition on some things and you still mess it up because there is a confounding effect. Now, shame is black here, but there was a paper a couple of months ago, or last year, I forgot, about a paper that got retracted on influence of gender and mentees and mentors. And some of the things that they had was related to this idea. Like they were controlling on some things or not controlling on some other things. So they might have been measuring some factors with more exaggeration than granted. Now, I don't know why. I mean, I won't share my opinion here, but I don't think the paper should have been retracted. It should have been like issue some sort of notice of, okay, there is some concerns and we'll modify the language. Anyways. All right, so going back to this intuitive example, we can think of these three cases with three different DAGs. Okay, so here, because X is actually generating Y, we have this DAG. Okay, so we have a direct connection, causal relationship between X to Y. In the other case, it's the opposite. Y is generating X, so Y is causing X, but we still see the same data. And in the third example, we have a confounding effect. We have a variable that is affecting both the input and output, or the treatment and the effect. Okay, so for some reason, this is not displaying correctly. So I'm like fix it in real time here. So if we kind of jump to the world of Julia Perel and his do calculus, I think it's very intuitive to think about how you want to think about what will happen in the world through interventions. Okay, so what will happen if we intervene in a causal graph? So what if we say, okay, let's try to see what the effect of the intervention will be. So let's say, let's fix the value of x, let's fix the value of x here, let's fix the value of x here. And we will like to see the effect on the graph. But this is a causal graph. So I won't get into details, but if you know about statistical models, when you set a variable, you just condition on the variable and you will still have influences. So it won't tell you which of these models is correct if you have a probability distribution. So this is different. This is causal. Now, Julia Perel is always talking about how easy this is, but he's a genius of the highest caliber, so nobody can understand really. Well, nobody understood him for 30 years, I think he was saying, yeah, we should do this, and nobody pay attention to what he was saying. But this is what he was saying. He was saying, if we do an intervention, if you do a do x equal 3, you basically change the model in this way. You set x to 3 everywhere, okay? Now, what's cool about this is if you do this with the data, you can see that the x changes in x will shift y. You see here? So you set x to 3, and there's a shift in y. But in the others, there is no shift. You see like sideways. Here there was a shift, and here there is no shift. So you will say that in this causal, graph, there is an influence between x. The x is causing y, because if you intervene on x, that causes a change in y. And my fabulous example of the temperature and the thermometer, you can try this. If you change the temperature outside for some reason, you're God, that will change the temperature in your thermometer. But if you change the temperature in the thermometer, if you kind of change the mercury into all those old thermometers, that shouldn't change the temperature outside. That would be nice, but that won't happen. So this is the same idea. All right, so let's see. I'm fixing this because it's all messed up. All right, so there are many methods of once you detect what kind of things you have to control for in causal graphs. Okay, so you have to say, okay, what are the things I have to do to close all the backdoors to meet the backdoor criteria? So you say, okay, I have to block, let's say in this case, I have to block the influence of Z, right? So I have to block that because this backdoor is open, okay? So once you decide that, you can apply a number of techniques, and there are many techniques, and they are appearing every day. And this is where I think it's very important to learn both sides of causal inference. There is the kind of machine learning AI side and the statistical side, because the statistical side, the methods are much more well developed in my view, and this is my personal view. Whereas in machine learning, it's all like unclear. It's beautiful theory, but it's unclear how to apply it. So one of the techniques that I will talk about is called subclassification. Yeah, maybe. Yeah, Julia is saying Julia Perel will not. Well, there was a proof. So there was a paper that proved that the two things, and I for some reason I met his student 10 years ago, and I told some jokes that I shouldn't have. But anyways, but there was a proof around that time that showed that it was the same. But maybe, yeah, maybe he will feel like one of the things that is nice about Julia is that he created these awesome graphs, and this is just so much more intuitive than the equations that Rubin created. All right, so the subclassification idea is that you can measure things about your units. So these X are things that are external to your units that make the treatment independent of the potential outcomes. Okay, so this if you have this, if you can make this assumption, then you can apply something like subclassification to make the inference about that. So you have that, and also you assume that the probability of someone getting a treatment for any value of these other covariates, if that's always possible. So it's not always 1 or it's always 0. If there is always a possibility of someone getting a treatment, no matter what kind of covariates, then you have these two assumptions. Then you can apply subclassification to control for that backdoor. Now the method is a little bit, I'll advise to read the book, but basically you're saying, I'm going to split my data into little pieces, okay? And then I will find the different effects in those little pieces, assuming that within those blocks, those cells of data, things should be the same. There shouldn't be an influence between the treatment and the outcome. Okay. Now there are many other methods, and Jin Chuan was talking about propensity score matching, and this is coerced exact matching is a very popular and really powerful. A lot of papers I've seen in Science of Science are applying this method, and the paper that got retracted, unfortunately, they apply that method. It's a perfectly reasonable method. There was nothing wrong with the paper, in my view. It was just that they didn't control for some things, and I mean, methodologically there was nothing wrong. Anyways, you have regression discontinuity, very powerful. I think Dashun's paper on setback, like this idea that if you get a grant rejected in the future, you will get stronger. He applied regression discontinuity. Matching, we have Aaron, he applied for showing that if you move to a better university, if that's a treatment, let's say if you go to the best university in the US, that gives you a lot of advantages. It's not just your ability; it's just the fact that you're in a better university. And he used matching for that. So that's another way of showing that there's a causal effect, not just correlation. All right, so I have a little example here. I think, well, this is my opinion, but you should maybe look at the paper. But basically, I think they were not controlling for some things, like so there were some backdoors open, basically, in their analysis of the paper, and I think the effect would still be there, but I don't think it would have been that big, and the effect wasn't big to start with at all. So the paper was like overblown a little bit, in my opinion. Anyways, so let's so this is now this. Oh, I got cited twice. Wow. Science happening in real time. Now read the original paper, the retracted paper, and it's always I think good to read those retractions. All right, so I'm going to look at the Titanic disaster, and I'm sure you're all familiar with that. Now, one of the things that people have been wondering for a long time is the effect of getting a tick of being in a first-class cabin in the Titanic. Did that increase your chances of surviving the disaster? Okay, so usually I recommend, and by that I mean, Microsoft recommends these 3 steps, and I think they have like a 4th step where you kind of check things. Is to first you establish a causal model, and again, this is a philosophical model. I don't think we can argue that you can infer this from data. This is just okay. You assume this is what's happening, and then you say, I'm gonna identify a way so that I get rid of the confounders and colliders that open backdoors. That's called the identification criteria. And then we can do causal inference with all the methods that's I list here, any of the methods here, well, depending on the kind of data that you have. Okay, but I will try it with the subclassification example. All right, so the first step is to establish a causal model. Okay, so this is an assumption that I'm making, and by that I mean the book that I'm using to present this. And the assumption is that yes, you have a causal relationship between D being the class, so first class will be D equal 1, not first class will be D equal 0, and the outcome, which is survive or not survive. So Y1 means you survived the disaster, Y0 means you didn't survive. So yes, there is a direct causal effect, but there are these two confounding effects. One is that women, well, this is an assumption, women tended to be more in first class, and also they tended to survive more because at the time, I think the custom was to let women go first, for example, into the boats of rescuing. So there was this confounding factor related to gender. The same thing you could say about children. Okay, so this is the age of someone. So C equal 1 means it's a child. So a child will go in the Titanic only if the parents were rich. So it would be much more likely to be in first class, and also because of the customs at the time of our world, it will be more likely to survive. So there was this thing affecting both things. Okay, so if we don't pay attention to these confounding factors, we can make mistakes. So let's look at those mistakes. Okay, so I'm going to read the Titanic data set. Okay, something happened. Okay, so let me see. I need to fix this in real time. So hopefully I can do it. I have the data here. Excellent. And if I'm quick enough, I can create a folder, call this data, and upload. Causal inference data. I'll upload the data. Perfecto. And then I'll read this. Perfect. Okay, so this is the data. I rename things with numbers so that it's easy. So class, we have all the class. We have ages, sex, whether you survive or not. So Y will be whether you survive or not. D will be the treatment, so first class or not first class. W will be woman or not woman, the gender. And C will be child or not child. Okay. So if I measure the naive relationship between class and whether you survive or not, it's a pretty big effect, right? So it's like if I just take the observation data, it will be 0.5 something minus 0.3. So it will be like a pretty significant difference between these two. So the observed difference between the outcome of the treatment and not treatment will be substantial. Oh, I have it here. Okay, so I don't need to be looking at the graph. So it's 30%. So the chances of being in the first class compared to non-first class is 30% more chances of surviving. Okay. So I will apply subclassification, and the method is a little. It looks a little intimidating, but basically we're saying, well, we want to control for this thing, for the gender, and we want to control for the age, basically. So I'm gonna kind of separate my groups of people into cells where in one cell everybody will be of the same gender and same age. Okay, so everybody in one cell will be women and children, and I will see within that cell the differences in the treatment and how it affected the outcome. Okay, so because I'm assuming that this is the relationship, the causal relationship, I can do that splitting, and it kind of helps fix that issue that I had these confounding factors. So this is what this code is doing. Okay, the code here is doing, I'm gonna kind of group things by gender, that's woman or not woman, and age, and then I will apply a weighted average effect within each of the cells, and then I will sum all those effects. So at the end of all of this, what I will get is that actually, if I account causally for the effect, the confounding factors of gender and age, the chances of survival is only 18% more if you are in first class. So now I'll finish by saying that this method is relatively old, and I don't think a lot of people use it these days. It has a couple of issues, CEM seems to be pretty general and applicable. In Python, we don't have a lot of these methods implemented, so R is much better at this. They have a lot of packages for doing each of these. In fact, most of these methods come from statistics, so a lot of the packages are implemented in R. So if you want to do causal inference for now, maybe do them in R. And with that, I'll finish my presentation. I don't know if there are any questions. And Pearl, he has the causal inference book. This book, Causality, it's actually. Now, one of the most amazing things about this book is not the theories. The last part of the book has like 20, 30 pages of philosophical discussion about how the history of humanity has been avoiding to do causal inferences because fundamentally it's not possible. So you have to make assumptions. So philosophers have been like avoiding to do those kinds of jumps. Yes, too many things happening. Hopefully this is being recorded. And again, I've been learning this, and it's just unintuitive. It's unintuitive. I prefer to go back to machine learning.
Just get more data.
Get more data, yeah.
So Daniel, I express confusion as well. I was trying to think back to the sort of doctor treatment, I guess bias question, and I guess I'm still having a little bit of trouble distinguishing between bias and noise, especially if you have like a randomized sample where you're, if you're blindly choosing a treatment based on, flip of a coin. How is the result going to be biased rather than just noisy because of some covariate?
Well, if you're choosing treatment at random, is that you don't have problems. There's no bias.
Okay. So if you do randomize, then you're fine.
Yeah.
Okay.
If you randomize,
it's just that in reality, that's not how it works.
In reality, we have these mentorship data sets and citation data sets that we
don't. Mentorship choices are random, right?
we should make them random. We should force people to mentor with someone. Yeah, but if you see the if you kind of randomize the assignment, you have these two consequences. Mm-hmm. So the selection bias goes away, mm-hmm. and the other kinds of bias also goes away. So at the end, what you measure in the data is the average treatment effect.
Right. Okay. But so the problem is that that's just not how it happened. Like only in a controlled study, you're doing that, exactly. I guess, as well as you can. But,
yeah.
And if since the gender paper obviously is relevant to some work that we've done, so I guess I'm a little bit confused about the criticism, right? Because the paper did take the approach of balancing, performing the same manipulation that you were doing with the Titanic data, right? Or at least they claimed to.
Yeah.
But was the criticism that they didn't do it effectively, or
the criticism is that there might be things that are not directly causally related with gender. So,
right.
At least what I criticize was that women tend to advertise, and this is broad generalizations, and apologies for doing this generalization, but certain genders are less, they advertise themselves less, and that affects the citations and things like that. So yes, you could have a causal effect, but it might be indirect.
Right. Yeah, which is, I mean, that's, yeah, obviously if there are variables that you haven't identified.
Yeah,
obviously.
and there are things related to the prestige of the institution. I think they control for that. I think one was funding. Yeah, so.
Right. And it's arguably, I mean, yeah.
Yeah.
That's, I mean, that's sort of in our, I mean, the study that basically has the same results, but you know, in our preprint, we basically found covariates that it could explain some of the effect. So it seems like,
Right.
I guess that's I mean, yeah. So I sort of feel like in terms of the criticism that you're posing, that's something that we've been dealing with. Yeah,
approved. Yeah.
All right, there's a truck going by outside.
Yeah. Now what's crazy is that can we really collect causal relation with matching methods such as probability? Yeah, I made that comment, Julio. That's me, which is funny. I was a reviewer of that paper. I was the only one that chose to be public, so I was pretty embarrassed when everybody was on Twitter. I was, oh my god, the Twitter mob is coming for me, and then people started saying this reviewer was awesome, and I was like, yes, that's me. So I took the opportunity. Well, one of the things that they did, which I think your paper is better at, Stephen, of course, is that you have a mentorship data set, but the paper didn't have a mentorship data set. It was co-authorship. Now it's pretty close, but it's not capturing everything.
Right, but that's a secondary. Yeah. And the point is, you need to acknowledge the unknown variables. I mean, and I don't know if that was the sin of this paper, that they kind of, you know, the conclusion was don't work with a female mentor or something, and
yeah, I think they overclaim it. I don't think they should have. I think in the abstract they said, you know, like, I mean, they tried to tone it down by saying association, not causal relationship, but it was just, and it's a controversial subject too. I think they published a similar paper before, but it showed like something that wasn't as controversial, but it was still the same method.
Right. Well, no, that was actually, they showed a beneficial effect of diversity, like I think it was ethnic diversity in co-authorship groups. So it's basically the exact same analysis looking at you know, diversity, and it was beneficial, and everyone was very happy with it, right? So I guess, yeah, you could lodge the exact same criticisms against it. So yeah, that sort of was a kind of bizarre sociological confound.
Yeah. Yeah. It is a bias. Yeah.
Thank you, Jody. Yes. So it's the science of science again, I guess.
Yeah, we should definitely, that's a paper that we should work on. Yes. What was the other thing? Yeah, so Yifan is mentioning propensity score matching. So the method that I use is different from propensity score matching. There are a lot of issues with propensity score matching, and that's one of the questions that I asked Jin Chuan, which is when you do propensity score matching, you kind of transform this very high dimensional space of the features that it describing a scientist, for example, to just one number, which is the probability of being in the treatment. So you squeeze all of this very high dimensional space into just one little number. So when you do the propensity score matching, you might have people match in probability, but then some features are completely different from one another. So you ideally want to have the same similar people. Like here in the Titanic data set, you are saying, okay, we want people compare within the same cell, like the same gender and child, and then you compare the treatment. But when you do propensity score matching, these things could be like wildly different, and it won't care. So cool. So why don't we take a break, like a 15-minute break, and then we'll have the presentations. your proposal presentations. And what I will do, I will again project them on the screen. If I messed up and you say, oh no, I don't want to go up, just let me know and I can just go to the next. Okay, no problem, no pressure. We are all here trying to learn. There's no right or wrong project. It's just all, we're all just learning things here. So